Welcome to Debug Diaries by CSC, a podcast where we dive into the world of technology with some of the most influential minds shaping its landscape. Join us as we explore the past, navigate the present, and envision the future of innovation and technology. Today, we are excited to introduce Mr. Thilina Ratnayaka, a researcher specializing in high-performance computing. He has been part of a group which was instrumental in advancing fluid simulations on supercomputers, achieving groundbreaking results on the frontier supercomputer, leading to a nomination for the prestigious Gordon Bell Prize. His work exemplifies the cutting edge of the computational space, pushing the boundaries of what's possible with modern supercomputing technology. So, good afternoon, Mr. Thilina.
Good afternoon. I'm happy to be here.
Yes, we are really excited to have you on board our podcast for today. And we are sure that our viewers will have an exceptional treat getting to know about your story and what you're doing in the technology world. So, before diving straight into supercomputers and high-performance computing, I'm sure our viewers would like to know something about your early days. So, what was it like growing up, and what led you on your current path?
So I grew up in Kurunegala on a small village. Uh, I somehow managed to pass grade 5 scholarship examination, which gave me the chance to get into Moratuwa College, which was really helpful because I met a lot of smart people there, which improved my abilities. And somehow, with the help of those friends, I was able to get into University of Moratuwa. And during University of Moratuwa, I did a couple of projects which kind of pushed me to the research what I'm doing right now. So at the time, Google had something called a Google
Summer of Code?
Google Summer of Code, and I participated 2 times under SimPy organization and SimEngine organization. Both of them did symbolic mathematics, which kind of pushed me towards using computers to do mathematics. So that's how I ended up here. Yeah.
Right. So, as you mentioned, you joined the University of Moratuwa. So, you are from the Department of Computer Science and Engineering. So,
Yeah.
what drove you to select joining into this department?
Yeah. So when I was in high school in Moratuwa College, we had like a computer club there. So we used to hang out with some of their older students, and they taught us things like programming with C's, Pascal, and I was really fascinated by that. And I really loved solving IOI problems, Informatic Olympiad problems. So that was something I really enjoyed. So I decided if I get the chance to go to University of Moratuwa, I would do computer science.
Okay. So you are part of this internet, the technological landscape at around 2010s, if I'm not mistaken.
Yeah.
So that time it was quite different from how it is now.
Right.
So how was it? What were the key players? What sort of projects did you do when you started off at University of Moratuwa?
I think at the time, the most of the focus was on object-oriented programming, mainly Java, not even C or C++. I think a lot of companies at the time was just outsourcing companies, and except for maybe WSO and a couple of others who were like doing some original work, but most of across the industry, the widely used language was Java, and widely practiced program model was object-oriented program, which is completely the opposite what I'm doing right now, because object-oriented programming doesn't play nice with high-performance computing in general. So yeah, that was the landscape at the time. WSO was unique in a way because they had their own products, but they're still using Java because it was platform independent. They could write their middleware using that system and run anywhere. Yeah, that's pretty much what I remember. And there was I guess Millennium IT who did kind of high performance trading platforms. I think they were heavily using C++ and language like that. Yeah.
Right. So back in the day, could you tell us a bit about your favorite memories from the Department of Computer Science?
Yeah, I think I had quite a few. I think CSE Hit the Grounds was very famous because it was cricket plus there were a lot of sponsorship, a lot of foods to go by. So I think it was a really fun experience. I remember there was a drama festival as well, CSE drama, which I haven't done anything like that in my high school, but I somehow participated with a group of students, which was, I'm a bad actor, but that was fun. Um, but mostly the best memory I have from my undergrad is basically the friends I met from all over Sri Lanka, and I'm still friends with a lot of them. So it's friends, hanging out with friends, learning with friends, and like doing fun activities with friends. I think that's probably the biggest highlight. Yeah,
Yes, and I think we all can relate to
yeah,
how the people around is that what makes that place special.
exactly. Yeah.
So, could you say something about like the Department of Computer Science and Engineering that helped you and we would say pushed you towards the career path that you are on today?
Yeah, we had like pretty good professors who were like very knowledgeable, and I really enjoyed some of the courses, especially there's a programming language course offered by Professor Sanjaya Sooriyarachchi that I really enjoyed. There are a couple of parallel programming course and a distributed programming course offers. I think it's by Professor Dilum Bandara. Those were really, really fun courses. I really enjoyed them, and they all always were willing to help, and they always wanted us to do more. Yeah, so it was really they were like pushing us to explore new things.
Right. So I think it was those foundational courses that you were offered to you at the department that really piqued your interest in this field of which you are currently in.
That's true, and as well as like contributing to open source projects. I think that's really important. You get to learn a lot that you don't learn in your university as well. So yeah, university is definitely important. There were lecturers who were like giving us solid background, but contributing to something open source, you learn a lot of stuff that you wouldn't otherwise learn. Yeah.
So now that we've spoken about your early days, could we talk about what you are working on and what exactly is it based on?
So right now I'm still working on high performance computing. Now I work at Argonne National Lab. Basically, my job includes try to support scientific applications on these up and coming and state of art computer platforms, basically supercomputers. So in US, a national lab would get a supercomputer like every 4 years, every 5 years, a state of the art computer which is capable of doing a lot of calculations. So right now, Argonne is getting a supercomputer called Aurora, and it's going to go public very soon. And I'm helping some of the applications run efficiently there. And apart from that, Argonne is like a pretty relaxed place where you can do your own research, try your own things. So I'm trying, like experimenting and researching about parallel programming models, like how to portably you what kind of program models are there which are portable and which are performant and which improves programmer productivity. We call this 3P, like performance, portability, and program productivity. So I'm exploring those things, and also I want to learn new things. So I do whatever I feel like I need to learn. Yeah.
Yes, that is a really cool philosophy to follow.
Yeah.
But I think for our viewers, I think they would like to know a bit more about these high performance computers or supercomputers, as you call them,
Yeah.
and what differentiates them from the normal computer that we use in day to day life.
So a normal computer would have like a limited amount of memory and a limited amount of processing power. You would realize this like if you start doing like a really big calculation on your laptop or a PC, it will take forever. What a supercomputer essentially is, you replicate your laptop or a PC, but connect them each other with like a high performance network so they can talk to each other to collaborate on solving a problem. So what you get eventually is a lot of computing power and a lot of high bandwidth connectivity. So you can port your applications and run big problems on these supercomputers. So a problem that takes like 3 months in your laptop probably could be done in like an hour within a super well, less than an hour. Yeah, for sure. So things like that. So they just give you enormous access to computing power, so you can run much larger problems efficiently and faster.
Well, that is really mind blowing to hear about the exponential gain in performance that you get between a supercomputer and a computer we use in day to day life.
Right.
So, could you tell us about an example, a real world example that a supercomputer has solved in according to your knowledge?
So there are a lot of applications in supercomputers. Mainly, I have been working on computational fluid dynamics simulations. Those things come up in aerodynamics, or when designing nuclear reactors, they have to do these simulations. Also, they have been used in climate modeling and weather prediction. That's a big area where they use supercomputers to do, like, you need to predict weather real fast, especially like if there's a storm coming and it's developing. You want to really tell you very quickly like what's it's gonna do next, and like they predict the path. And there are even in AI, like these large language models that are like very famous right now, they're trained on like big supercomputers with a lot of computing power. Um, yeah, I think the applications are really endless. You could do a lot with supercomputer. What supercomputers basically allows you to do is solve large problems more efficiently. And with each new supercomputer, you get access to solving a much larger problem much faster, like giving you like really good information super fast. Yeah.
Right. So, since you mentioned about these large language models and AI, I think something that has been pretty famous or pretty popular these days has been GPUs
Yeah.
and the distributed architecture of them and how you have different paradigms to program in them.
Right.
So, are they also related to supercomputers, or are there differences?
Yeah, they are definitely related to supercomputers. So maybe a decade ago, not so much, because decade ago GPUs were not like a mainstream commodity. It was like very niche market. But now they have come out from the original application, which was like game development. Now they are everywhere. Now pretty much every supercomputer in US that you get are like GPU based system. If I'm not mistaken, 9 out of the top 10 systems in the top 500 list are GPU-based supercomputers. I think the only CPU-based supercomputer is the um, machine at Japan, which I cannot really remember the name right now. I could be wrong with the latest list, but it's uh, most of the computing power in the top 500 list is dominated by the supercomputers. So in case you don't know, or the viewers don't know, top 500 list basically ranks the fast 500 supercomputers, publicly available supercomputers in the world. So yeah, I think most of the compute power of the top 500 comes from GPU based systems right now.
So right. And there also has been a bit of a buzz about this quantum computing, which we've heard of many of these tech giants
Right.
doing research on, such as Google.
Right.
And even we heard about their recent deployment of this supercomputer called Willow, if I'm not mistaken.
Right.
So, do you think quantum computing would eventually take over supercomputing, or would they go hand in hand? So, what are your thoughts on
Yeah,
this?
so I'm not a quantum computing expert by any means. I hope there will be like quantum supercomputers, right? Just as there was like regular CPU based supercomputers, I hope there will be like quantum supercomputers that you can use. Um, for sure, they are faster for certain tasks, like probably faster for certain tasks than traditional computers. But I'm not sure whether they will be faster in like every case, or like whether they will entirely replace the traditional supercomputers. That remains yet to be seen. GPUs haven't completely replaced CPUs, but they are more similar to each other than they are to like quantum computers. And I actually quite not really an expert to predict on that. I think it's really hard to predict future, especially given that a lot of smart people are working on different things. But I'm pretty sure it will be a success because a lot of smart people are working on it. A lot of companies putting their money on it. But to what extent is, I think, has to be seen. Yeah.
Right. So, in your field, I'm sure you have to work with people of different fields of expertise, such
Yeah.
as physicists, mathematicians,
Yeah.
and engineers. So, how do these collaborations work, and which other fields do you collaborate with?
So I mainly work with physicists. Uh, it's actually pretty challenging task to collaborate. I didn't have, I don't have a physics background. I just have a computer science background, and physicists, some of them don't have a computer science background. They just have a physics background. So talking to each other is like obviously a challenge. So it's really a must to like develop some common lingo where you can like talk about things and share your knowledge. um, but there are certain cases where like computer science is turning into physicists and like figuring out everything so they can like act as mediators, or the physicists can it could do the other way as well. Physicists can get really good at computer science. But I think the best way to do collaborate with these different experts is to have like something called a co-design, where co-design is basically you get together and design things together. Like if you are designing the next supercomputer, you get together with the software folks, you get together with the hardware folks, you get together with the application engineers, physicists, and you meet every, say, week or every month or like every year, and then you share your knowledge, ask each other problems, and collaborate. So co-design, I think, is a very important thing, where so everyone is involved in the decision making from the very beginning, so people know what they're getting when the supercomputer is deployed. Apart from that, I think one of the very efficient ways to collaborate is to come up with like benchmarks, like very simple benchmarks which everyone can understand. Like rather than words, just verbal words, you write some code, and you share it with computer scientists who are like could be software engineers or hardware engineers or network engineers, file system engineers, whoever that is. You share that benchmark with them, so they don't. There's no doubt, right? There is the benchmark. You can always run it and test it. Same goes for the physicists and other scientists as well. There's this benchmark, so you can always look at it. So that's a really effective way to collaborate, because if you have a problem, you can look at the benchmark, try to reproduce it, and see if you can explain it to the other person who is familiar with the benchmark. Another would be a slight extension of the benchmark called like a mini app. It's slightly, in a sense, it's a benchmark too, but its mini app basically is like a watered down version or a very simple version of an actual physics or actual scientific application. So rather than the full application, you boils down that application to like the things that are most important, or things that are most costly, or things that are most important. And then you can do the same collaboration through mini apps. So you don't have to know. So computer scientists wouldn't need to know too much about actual science or scientific method there. Just have to familiarize with the mini app. So that's pretty effective too.
Right. So, since you spoke about collaboration, could you give us an insight into how a team that would take part in a typical project for involving supercomputers,
Right.
and which what about the diversity? Like, where do people come from in one of these typical teams?
So yeah, definitely they have diverse backgrounds. Uh, there are mathematicians, there are physicists, there are computer scientists, and they are at least in the projects I have been part of. It was mainly like local to United States, because the projects were funded by Department of Energy, and they were basically collaborating different universities within US and national labs uh, to um, to come up with the solutions or come up with planning the next computer. There's definitely diversity in opinions. People tend to have very strong opinions, and they have certain set of beliefs that they stick to, and they fight for it, they debate for it, and it's very active in that sense, which is really good. rather than like going with a single voice, having different opinions about even the even the things you might appear very trivial in the beginning. Having those debates is really important because it clarifies the problem and it lets you develop a perspective that you didn't have before, and eventually it furthers science. So I have been in rooms where people like they like almost like yell at each other, but in a like a very friendly way. They they stand up for what they believe in, and they when they're wrong they accept it, and when they're right they share it with others, so that a lot of scientific progress can be made that way. Yeah.
Yes. So, could you also enlighten us on what a typical day looks like to you when you are involved in a project such as involving supercomputers?
Yeah. So if I'm benchmarking a certain application for performance, it's basically involves like, okay, why is it not performing well? So I need to find hot spots of the application, in a sense, like which parts are taking too much time. You can use tools like profilers to do that too. Um, but it doesn't have to be that complicated. You can do binary search, right? Like say you initially split the code into two sections and see like which one is taking more time. Just keep searching like that. It doesn't take too much of time, and it's really fun to do that. So if there are like hotspots that you identify, even with a tool or like even with simple strategy like that, then you have to figure out like, okay, why is it not performing well. So one thing is to just verify that it is not performing up to your expectation. So you have to have some kind of a theoretical understanding of what this operation should cost, and then like you do what you call like a back of the envelope calculation. Say, okay, this is doing this much operations, and this processor is this much fast. I should be getting this results like this amount of time, and I'm not getting that. So then you can further explore more. Like, good thing about computer science is like it's definite. Like, you don't have to guess, in a sense. Like, you can estimate to like a very good degree like how much this operation should cost. And if your expectation doesn't, like if the reality doesn't match that estimate, you can delve down for, like, you can go further. So that's, if I'm struggling with the performance problem, that's pretty much what I do. I try to understand why is it not working as expected, and why is it not performing as expected. And then it could be an issue of the implementation, like simple issue, like you could have done something really um, stupid, I guess, and which takes a, like, you somehow implemented an algorithm that only costs like on in on squared time, like that could happen. So in that case, it's an easy fix. If it is not, if the algorithm itself is like not good enough for that application, then you'll have to probably research new algorithms to solve that problem. It could be like it could be if the like maybe you have to, like, even if you cannot come up with a new algorithm, you might have to rethink the whole thing as well. So there is like a lot of levels to it, but you can start at the really small things and work yourself up to fix the problem. So if I'm like doing some performance debugging, that's what I do. But I always get the time to, like, at least now I spend some time like experimenting new things. So in that case, I'm like very free. I just try different things, coding different things, evaluating different things, and see how it feels like, and try to come up with something that somehow could get like the best of two approaches. Say like there are like two ways to do it, but somehow can I come up with something that's like that has both those good qualities.
Right. So, while we talk about high performance computing, could you also tell us about a common myth or misunderstanding that people have about supercomputers?
Yeah, I think a lot of people, I don't know how much, but I'm going to say a lot, but people think that the high performance computing is incremental. Like you implement an algorithm for like a single process, and just then you can do it for the two processes as well. So they think like going from one to two is incremental, going from two to four is incremental. and 4 to 1,000 million is let's just incremental progress, because the hardest thing is like implementing the original algorithm itself. But I don't think that is true. I think that's a myth. At the fact that you're increasing number of processes, I mean, you are probably increasing number of problem sizes as well, and you're probably running on a different machine with a different architecture as well. So if you are operating on different regimes of the problem, different regimes of the hardware, a lot of new things come up, a lot of new challenges come up that's just not incremental. You have to rethink all the original algorithm. So something that is maybe a good serial implementation may not be a good way to implement that in parallel. So it's not like you okay if even if you have something that works really well for like 1,000 processes, when you go to like a million, it's probably you need to redesign the thing. Um, I think that's one of the myths people have, that this is just incremental. I can give you an example as well. Like when people started scientific computing or at least fluid dynamics, they could afford to invert a matrix like uh, without thinking too much about it, because the problems are so small. Then as the problems grew larger, their linear systems grew larger, then they have to come up with like smart tricks like reordering the matrix, and maybe using new algorithms to say like invert a system. And when it became much larger, they had to completely move out of this direct, what you call direct methods, and come to like iterative methods and develop precondition and things like that. So it's not incremental at all. If you run a problem at scale, that means like you're facing a lot of challenges.
So I think I'm sure that is like a good debunking of the myth that you have shown us. Well, I'm also sure that many of our viewers are aspiring undergraduates who are looking to pursue a career in high performance computing.
Right.
So, what advice would you give to aspiring undergraduates who are looking to pursue a career in supercomputers?
Yeah, I don't know the status right now, but when I was an undergrad, we didn't have a lot of um, resources to do high performance computing. Yeah, I think we had like one GPU for the entire department. I don't know the status anymore. But so it's really hard to get into high performance computing with that kind of lack of resources. So what I would encourage for someone in Sri Lanka is definitely reach out alumni, or reach out, like talk to your professors and see if they can connect you with people who has access to better resources, and try to do something that could like help you move in that career path, like maybe a project that could help you in getting a PhD, or a project that could help you getting a job position in the industry. So I think that's probably the thing I recommend. But even with few resources, you can do research, and that's what I did too. Like we had a one GPU, and somehow we one maybe two, somehow we managed to do some research. So um, I think you can always try to think about smart ways to do things like that. And also, I would encourage to like reach out to general resources available public. Like there are a lot of resources for any topic in the world right now. So try to find those projects, collaborate with people, and you'll probably get access to those resources as a result as well. So I basically try to reach out to people and try to use resources that are already available in a very efficient way, I think.
So, as we're about to bring to close today's podcast, it has been really great having you today with us. How do you see supercomputers changing in the next 10 years? And what do you think they can do that they can't do now?
Yeah, so 10 years is a very long time to predict the future. I don't think anyone can get it right. For example, in 2015, no one would have thought like the development of LLMs, or like how yeah, I don't think anyone could have predicted most of the things we have today. What I can tell you about supercomputing is that the trend has been like you always get much more powerful supercomputers every year. So supercomputers 10 years ago is like toys compared to the supercomputers now. I think that will be true another 10 years from now. The supercomputers we have today will be look like toys compared to the supercomputers in 10 years. So that means like the people will be using them to solve much larger problems and much faster. That will help them advance scientific knowledge faster, and that will enable them to do many discoveries. So I think I can guarantee that will happen. But apart from that, there are different strategies people are trying to like steer. Like some might experiment about it on like application specific hardware, where like hardware like similar to software, you write software for each application, and similar to that, you will like come up with hardware that is like cater to that particular application. So you get a lot of efficient implementations, and if like you can run them very efficiently. So people are experimenting on that, and people are experimenting on what do you call like in memory computing or near memory computing, processing in memory. Um, Basically, rather than trying to get data from memory to the processor where the processing happens, you try to process the data where the data is. um, Again, it's remain to be seen who will be successful, and it largely depends on what type of applications there will be in 10 years and what type of hardware will be most suitable to run that application. But for definitely, we will be have much larger supercomputers, much powerful supercomputers that could help us solve large problems.
So that is really exciting about what we have in store in the next 10 years. And so once again, thank you, Mr. Thilina, for being with us here on Debug Diaries and giving us some very insightful thoughts on the world of supercomputers. So we thank our listeners here today as well for being with us. And we hope you have got something you've learned something useful today, and we hope to see you soon on the next podcast as well. So stay tuned on Debug Diaries. Thank you.